Hello again. This is a video solution to problem 7 from Superquiz 2. And here we're going to be computing some Laplace transforms and just by using the table, which I've put over here on the right. Now, it's not the entire table. The things that I haven't put in here are the Laplace transforms of derivatives, but there aren't any in this problem that we're going to be worrying about. So let's try A and B. Now, actually, B is going to be inverse Laplace transforms, right? You can see that little -1 exponent, which means we're actually going to be using the table from right to left instead of from left to right. So let's try A. So remember that the Laplace transform, right, is linear, which means you can break it up over sums and differences, and you can even pull out constants. Right. So this 2, I just pull that, like I could look at the Laplace transform of 2 and then pull the 2 out. So I really only got to worry about the Laplace transform of 1. And I can get the Laplace transform of 1 by using the top line of the table when n is 0. All right, so I would have t to the 0 is 1. So this would give me 0 factorial, which is 1, over s to the 1. So it's just 1 over s. So the Laplace transform of 2 is just going to be 2 over s. All right, what about this next one? Well, let me copy the 7 since, again, that's just a constant. And I have a cosine times an exponential. So the second line, and this is your first shifting theorem, says that if you have some function and you hit it with an exponential, all you have to do is take, okay, so f here, right? Recall that big F of s is the Laplace transform of f. I just need to take the Laplace transform of that function that I'm hitting with the exponential, so in this case cosine of 5t, and then do a little shift. Right? So what is cosine of 5t's Laplace transform? Well, I go to this line, and that says I take s over s squared plus a squared, where a is the coefficient of t. So in this case, my a is 5. So I'm going to have, well, tentatively, s over s squared plus 5 squared. Okay, well, easily 5 squared is 25. And why did I say tentative? Well, remember, I have to do this shift, all right? So the shift is going to be by 4. All my s's need to turn into s minus 4's. So s up on the numerator as well as in the denominator. So s minus 4 quantity squared. Okay. Again, very common mistake is to do s squared and then do the minus 4. It's not the same thing. You have to shift the input to the function, right? Not just put in s, square it, and then subtract 4. It's not the same thing. All right, then we have a hyperbolic sign. Hey, that just comes from this line in the table, so I'll have minus. Okay, what's my a? My a is 7, so I'll have 7 over s squared minus 7 squared, which is 49. Oh my goodness, this last one looks crazy, and that must be coming from this line. This is the second shifting theorem. I have some function multiplied by a unit step function. And the second shifting theorem says that if you have a function which has been shifted by an amount which matches the unit step function activation point, right? So these c's are matching, and hey, sure enough, right? Ooh, that looks pretty good. Then all you have to do is take a decaying exponential. Okay, let's do that. Decaying exponential, what's this decay rate c? That's the 6. Right, so I'll put that up here, 6s. And then I multiply by the Laplace transform of f. So I need to identify what my f is in this case. Note, this minus 6 is the shift. So if I want the f, I get rid of the minus 6. Right? That was a shift of the original function. So if I get rid of the minus 6, I just have t to the 4th. So I just need the Laplace transform here of t to the 4th power. And again, I can go back up to this top line. It'll be 4 factorial over s to the 5th. So this is 4 factorial, which is 24, but that's not important, over s to the 5th. All right, that's how we do A. Let's try B. So for B, we have first, ooh, what a mess. Well, this should remind you actually of our integration by partial fractions problem. That was 2b. We have this, there's no partial fractions to do here, but it does make sense to maybe complete the square here, because you notice we don't have anything that's a quadratic with an actual linear term in the middle. So let me take s plus 4 over s squared plus 6s plus 25 and rewrite it as s plus 4 over s plus 3 squared. So this is me completing the square, cut 6 in half to get the 3. And now if I square this out, I'll get a 9 as my constant, but I don't want a 9. I want 25. So I have to add 16 more. Okay. This is a little better because this looks like a shift, right? I can handle with the first shifting theorem. But if I was looking through this chart, okay, s squared plus 16, that looks like a sine or a cosine, but they only either have a constant or a variable s. They don't have both. So what I want to do here is actually split this up. Now, before I completely split it up, note this s plus 3 makes me think, man, I really wish this was s plus 3. Hey, I could just write that. Would anybody notice? Okay, as usual, yes, they would eventually notice. So I can't cheat forever. I'll put an extra plus 1 out here. So now I break this up as s plus 3 over s plus 3 quantity squared plus 16, and then plus 1 over s plus 3 squared plus 16. And so if I take the inverse Laplace transform, I can now do it piece by piece, and that won't be that bad. So this piece here, what is it the Laplace transform of? Right? Well, it has the variable on top, so that really makes me think it's the cosine, and yeah, it's just shifted by an exponential. Okay? So if I take the inverse Laplace transform of s plus 3 over s plus 3 squared plus 16, this will be the cosine of, okay, 16 is 4 squared, so I put 4t. And then how much am I shifting by? Well, instead of a minus, I have a plus, so this must be negative 3t. Okay, what about this other piece? Well, that's 1 over s plus 3 squared plus 16. This almost looks like my sine Laplace transform, only that's a 16 on the bottom, which means my a is 4, but I need a 4 on top. Oh, check this out, right? This is really clever. I just turned a 1 into a 4. I don't think anybody saw. Okay. But I'll put a 1/4. In fact, I'll just pull the 1/4 all the way out. Now it matches, and I'll have 1/4 the sine of 4t times e to the negative 3t. Again, right, there's a shift here, so I have to use the first shifting theorem. Okay, so the sum of these, right, the sum of these will give me the inverse Laplace transform of the first piece. Right. Now I need this last piece here. All right, so what do we got? Well, there's an exponential in the Laplace transform, and that's pretty good sign that I'm looking at the right-hand side of the second shifting theorem. All right, so I have an exponential, and then there's supposed to be a Laplace transform of a function. Okay, which function has this as its Laplace transform? 3 over s squared plus 9. Well, that s squared plus 9 tells me sine or cosine, and the 3 on the top tells me it must be the sine. Okay, so this is the Laplace transform of the sine of, looks like 3t. Well, how do I use the second shifting theorem? So if I'm taking the inverse Laplace transform of, let me write it as 3 over s squared plus 9, e to the negative 4s. And this is the Laplace transform of sine of 3t. Then the inverse Laplace transform is just going to be, we'll get rid of this L here. I need to take my function, which is sine of 3t. So sine of 3t, but the t has to get shifted. Shifted by what? Whatever this number is, this minus 4. So t minus 4. And then I need my unit step function at 4. All right. So in total, my inverse Laplace transform is going to be e to the negative 3t times, well, let's see, we'll combine these together, cosine of 4t minus a fourth sine of 4t plus sine of 3 times t minus 4. I could expand, like distribute this, but I'm not going to. Times u4 of t. And there we did it. We've used our table of Laplace transforms, first shifting theorem, second shifting theorem. Whew, what a workout.